Okay, I'm going to start with Gauss's law and Stokes' law. How many have heard of Gauss's law? If you have Gauss's law, you should have had it in physics. How about Stokes' law? Anybody heard of it or had it? Okay, Gauss's law involves the del operator, right? So you take the triple integral over a volume of del cross f, where f is any vector, and integrate it over the volume, and it's equivalent to the surface integral over that volume of f dot n dA. And that's Gauss's law. Okay, Stokes' law also involves a del operator, and if you do over a surface an operation we call the curl, which I'll talk about in terms of physical significance, if we do del cross f, which is called the curl of f, where f is a vector. And if I do this, I'm going to do it really similar to the area side in Gauss's law. I'm going to take the dot product with a normal to the surface and integrate it over the surface. So dA is a scalar surface element, and n is the local surface normal, and I'm integrating over the surface. So it's exactly like we did for the surface area side of Gauss's law. We're doing, instead of f, we're doing the curl of f, del cross f. And Gauss's law says this is equal to the integral of f dot dl, where L is an elemental length vector around a path. Yeah.
Could you explain what that means in like physical terms or whatever?
I will. I'm going to explain what it means in physical terms. So bear with me, I'll tell you. I didn't know where to start. I thought I'd start here and then go through it and then end up here in Ampere's law. So what we're going to do, think of it at this point, think of it as if I just introduced a mathematical operation. So at this point, rather than physical, think of it just as a mathematical operation. So as a mathematical operation, what is a del operator? So in Cartesian coordinates, it has three components. It's a change along x, the change along y, and the change along z. And if you have a scalar potential like voltage, you should have gotten that the E field is minus the gradient of the voltage potential, right? And so this has a form in different coordinate systems. It has a form in, this is Cartesian, and there are some length scale factors, either 1 over r for the theta term in cylindrical coordinates, and spherical coordinates there's a 1 over r term for the theta term, and there's 1 over r sine theta for the phi term. So these forms are in your book, and they're probably going to be covered in class. I'm not going to go through them right now. If you look at, do you know the physical significance of the del operator? Who can tell me the physical significance of the del operator? What's it measure? If I have a scalar voltage field, what does the del operator measure? And what's a name for it? I'll give you a hint. You're climbing a mountain.
Gradient.
Gradient, okay. The gradient's the rate of change, so it measures the rate of change. Now, where does that come from?
Charge distribution?
Let's say I have voltage, and let's say it's some function of x, y, z, right? How do I find the rate of change of voltage, or the total change of V? Take a derivative. How do you do it if it's a function x, y, z? dV is a change in V with respect to x along x, plus a change in V with respect to y along y, plus the change in V with respect to z along z. If you look at this, you can separate this and think of it as a vector that's a del operator all operating on the voltage. So the length, this dl in any coordinate system, is just the vector dx, dy, dz. So if I take that dl, I form the dot product, I get exactly this term here. So you could say it's the gradient of the voltage dotted with dl. So this gives a physical significance for the gradient. How many see this as a good physical significance for the gradient? See, it's a maximum rate of change, right? Okay. Don't be of the mindset that, you see this stuff. It should make some sense mathematically as an operation you could do, and it should make some sense physically as what the term actually means. So the mathematical operation is quite simple. You simply take the partial derivatives of the function, and the del has different forms and different coordinate systems. You have to make sure you get the right form. Now, if you have a vector field, you can also use this del operator, and you can do like del f, where f is some vector. And what's this called? What's del dot f called? And what's its physical significance? What's del dot E measure in the E field sense? If you had E field here, and this were del dot E, and this were E dot and dA, so we're just applying, making FE. What this says, this is called divergence. Okay, the divergence of a field is the net outflow out of a volume. So if you take a volume, the divergence, if you integrate over the volume, is a net outflow. If you look at the right side of Gauss's theorem, you're taking the vector, you're taking the dot product with the outward facing normal. So that measures the vector component that's normal to the surface, and you're just adding it over the surface. So the physical significance of the divergence is a net outflow. Okay? if you take Gauss's theorem and you apply it to a region that has no charges, what do you get? You integrate it over a volume that doesn't have any charges inside. What do you get? Zero, right? It's because there's no net field outflow. There's only a net field outflow when you have charges inside. Okay? So that's the physical significance of the divergence. Okay, now the curl, the next thing we're going to talk about is del cross F. This has different things it's called. It's called the curl, and sometimes it's called the circulation of the field. Okay, how do you calculate a cross product? Well, you take del cross F in Cartesian would be evaluating the determinant where you have unit vectors along the Cartesian axes, x, y, z. You have the change with respect to x, a change with respect to y, and the change with respect to z, and you've got fx, fy, fz. So the first row is the vectors, unit vectors along the axes. The second row are the vector components of del, and the third row is the vector components of f. Okay? And so if you want to evaluate the this, you'd take the x component would be the change of fz with respect to y, that's going this way, minus the change in fy with respect to z, and that would be along x. So notice it's along x. This is a vector product, where the divergence is a scalar, i.e. not a vector. This guy is a vector, so it's a vector product. So you could do the component along y, and it would be the change of fx with respect to z minus the change fz respect to x, and that would be along y, plus the change in f. Take the z component, it's fy along x, minus a change in fx along y, and that's a z component. So given any vector, all you have to do is evaluate that to get the answer. Did I make a mistake?
Should there be a minus over there for the product?
That's a minus. That's a minus.
No.
So you make sure this way is plus. So I've got fz. This way is minus, plus, and I've got the change back to y of fz going minus. I've got change z of xy. No, I'm sorry, that's x. So the y component is changes z of fx, and this is change x of fz.
Your y has to be negative.
Y, change with respect to x of fz. Yeah. I don't see a sign mistake. Do I have one?
The positive part of the y had a mistake. The y just had a
Up.
Yeah. No, he's right. You're right.
Think should be a minus.
Switch the.
If you switch the sign in the bracket,
That's, I mean, that's not a minus. That's an equal. That okay? So you thought maybe that was a minus? Are we okay? Are we cool? Huh? Okay, so basically these are the terms. So given any vector, you can evaluate to get the curl, which is called the vector product, del cross F. Okay, what's it mean? Okay, let's just consider the xy plane. So here's Cartesian axes, x and y, and z is coming out of the board because x crossed into y is z coming out of the board. Okay, so I'll note that as a head of a vector, that's z, he's coming out of the board. Okay, let's say I have a vector field here, some vector field f, and it's changing. And let's evaluate this side of the, we already know how to do that side. Let's evaluate this side. So let's say that we take a small element that in xy, this dimension is dy, and this dimension is dx. So here's a little element. Let's say at this point right here, the f has a value of fx, fy, fz. So it's a vector, it has 3 components. And at this point right here, then if I look at the value of f along this leg, the value of f that's parallel to this leg, we're going to be evaluating the integral f dot dl, and we're going to do this around a loop going counterclockwise. So let's say this is 1, this is 2, this is 3, and this is 4. So let's first get the value of this vector field on each side. On side 1, what's the value of the field? Okay, let's look at the value of Fy. So let's say, look how Fy changes. Fy, in terms of changing with x, Fy is equal to Fy here. Over on this side, where I'm just looking at the change with respect to x, it's Fy plus the change of Fy with respect to x dx. And if I did the same thing for Fx, I'd have Fx here And on this upper side, I'd have fx plus the change in fx with respect to y dy. Now the reason that I'm taking fx here is that I'm going to take a line integral. And when I do the line integral on this first side, the only term that it's along x. So the line integral on this first side, I do the integral of f dot dl, and I do the integral on the first side, I'm going to get f dotted with just dx times the x direction, because that's the x direction. So the first integral is just going to be fx dx. That's along this side 1. Along side 2, so this is 1. Sorry, I erased them. This is for 1. Along side 2, over here, I've got fy dy plus the change in fy with respect to x dx dy. Because when I do the integration of f dot dl along this side, I'm taking the vector direction is in the y direction, so I take a unit vector along y and I dot that with a field and I pick out the y component. So it's just that y component times the distance, which is dy. So this is along side 2, and if I do side 3, which is the upper side, I've got fx d and now the dx. However, the unit vector along that path is minus the x direction, so this is actually a minus sign. And I have also a minus, and I take this term, which is the partial of fx with respect to y dx dy. And finally, the fourth side, so this is the third side. And finally, on the fourth side, the direction for my dl along that path is minus dy. So I've got minus fy dy, and that one's for the fourth side. So the line integral of f dot dl is composed of these terms as I go around this elemental path in the xy plane. Okay? What's this equal to? Well, the fx dx cancels with minus fx, extra d there, sorry, minus ff dx. The fy dy cancels corresponding term, and I end up with just these two partial terms. So what I end up with is the partial of fy with respect to x dx dy. In fact, let me pull this out. I've got this minus the partial of fx with respect to y, and that quantity is times dx dy. So look at this term. If this were a small area element, what's the vector that's normal to that area? Well, it's a xy plane, so the z hat, or however you say it, the unit vector along z is normal to this area, right? So what we've done, we've shown that this term of the change in f with respect to y, change in fy with respect to x minus the change in x with respect to y, and this is the z area term. So this actually could have been written as a vector component, and if you did and look at it, you would, that's a Z term, you'd pick out exactly what we did when we evaluated the curl.
So what is this a measure of? Is this like voltage or charge?
It could be any field. In fluid dynamics, it's mass fluid flow. In aerodynamics, it's the air velocity across the wing. When you measure, if you take an airplane wing and you have a different distance on top than the bottom, you have a net circulation, because if you put it in a flow field and do the line integral around the field, line integral, you end up with a net number. And that net number, what do you think it is in the case of an airplane wing? It's a lift on the wing. So if you take a perfectly symmetrical wing and you put it in airflow, there's no lift. There's no up or down. If you make it further a distance around the top than the bottom, it actually gives it lift. So what does it measure in the electromagnetic sense? It's a good question. What would F become? Well, there are two things that can be measured. What vector fields do we have in E&M? We could apply it to the E field. Okay, so we could take del cross E. Has Professor Durgan talked to you about Maxwell's equations yet?
No.
Has or hasn't?
Yeah.
Okay. Well, you could apply it to the E field, and it would be del cross E, or you could apply it to the H field, and it would be del cross H. If you apply it to the E field, it turns out we're still in magnetostatics, but moving into time-varying fields, it turns out that it's a B field, and you'll learn how to relate B to H. In this case, it relates to the current. So it really relates to the enclosed current. And there's a second term for completeness that when physical laws were postulated, that term was let out, and it was thought of as a corrective term Maxwell put in, which is the change of electric displacement with time, which looks exactly like a current. So these are both current-like terms. These are two of Maxwell's equations. Okay, and hopefully as you go through, you're going to get all the other two as well. Yeah.
What is that dV.dt?
What louder?
What is that dV.dt? What is that?
The partial of time, it's a rate of change of time of the magnetic induction field, which you'll get. All I'm showing you is that the curl can be applied to E and H fields. And it's going to all come back when you get to the point where you tie it together, especially when you get into electromagnetic wave propagation. It's going to all come together.
It's so much like what the curl is an operator.
Have you had Faraday's law? I know you've had Faraday's law somewhere. Yeah, what's Faraday's law in physics? Okay, it relates something. What's it relate? What's EMF? Okay, so it relates electromotive force to something. What's that something? Minus the rate of change of the magnetic flux through an area. Okay? The point relationship is this. The electromotive force, the EMF, is a line integral of E dot dl. And so this is equivalent to that in point form from Stokes' law. So everything starts coming together, and I don't know the best way to teach it. My background came from the physics side, and on the physics side you kind of learn the math and then tie everything together. On the E&M side, sometimes you learn the physical laws and then kind of bring them back to Maxwell's equations and the math. And I'm doing it what is probably what I would think the easiest for you to understand. Calculate the curl. You can calculate the curl. Mathematical definition. What's the curl mean? Okay? Well, because except Stokes' law, I kind of showed one element of Stokes' law. In fact, I proved for the z component Stokes' law, because I related the integral of f dot dl to the curl del cross f, right? You could have done for all three components in general and show all the terms are the same, just as if you calculate it. So now you can calculate the curl. What is a curl? The curl is a circulation around the loop. So if you actually take and measure the circulation around the loop of a field, if the field's uniform, you have a field and it's exactly uniform, like this. Okay? If I take and do a path and integrate around that path, the integral from the bottom side of whatever this field is, take that component and add it up along the bottom, it's going to cancel the one along the top. The right side is going to cancel left side. So in a case like this where the field is uniform, the integral of whatever that vector is, dot dl is equals 0.
So like if we had a parallel plate capacitor, right, we would have almost uniform field in the middle and then it fringes out on the edges, right? So what you're saying is in the middle you have zero curl and it's just a measure, like on the outsides where it fringes off, the fields come around it, that's the curl.
Yeah, can you envision a flow in a river? Mm. Okay, so let's say you have a flow field going down the Chattahoochee. Okay, it depends where I do the curl, right? So if I were to do the curl around the whole symmetric part, I would get 0. But if I were to do a loop here, okay, I would have more going on this leg, the bottom leg, than with the top, right? So they wouldn't cancel. Okay, imagine a fluid flow and a boundary here holding it up. Which way is the water going to swirl? Clockwise or counterclockwise?
Counterclockwise.
Because when you measure the circulation, you're going to be at a bigger component down here than you are here. So you have a net circulation going this way. If I were to take a path across the entire river and it's symmetrical, I'd have a 0 curl. It would cancel. If I did one down here and did the same path, the circulation would be clockwise. I don't know if that helps. There's what people sometimes do is if you imagine fluid flow and you put a little paddle in the fluid, a little thing that'll turn. If it spins, there's circulation in whichever direction it spins. So you've been introduced to the curl operator mathematically. You've been introduced to Stokes' theorem, which you know how important Gauss's theorem is, right? So now you've been introduced to Stokes' theorem. Stokes' theorem relates the curl of a vector field. This is a vector product, so here's a vector and it's dotted with a surface normal. And it relates that to this line integral around a path. One last thing I want to mention on the curl is that we did it for an elemental path. Let's say we go back to our xy plane, and I did it for just this little element dx dy, right? So I showed around that one path how it kind of relates. Well, what if you had a big boundary here and you wanted to do the integral of f dot dl around that boundary. Well, you could break this into elements, so you'd basically do your integration over small elements, right? So let's take two individual elements, and you're doing the line integral, let's say, around this element. That's just picking one right here, let's say. And we're going to pick another one right next to it, and we do the line integral down this one. If you look at the terms that would arise for the adjacent sides, the term from the right one would cancel the term from the left one. So when you apply, and if you were to do this little elemental thing that I did, and you did over the whole area, what you're going to do is it's just going to be the periphery of the area. And that's where it comes in that the line integral of, let's say, the H field around the periphery is equal to over the surface of del cross H dot n dA, where n is the unit vector normal to the surface and dA is the area element. In Cartesian, this would just be dx dy for that plane. What's the integral of V dot dl? What is it from Faraday's law? It's a time rate of change of the magnetic flux through the area, right? What is it if there's no time rate of change of magnetic flux? 0. Okay, there's a special case if the vector field, a closed path in a vector field, if it's 0, it can be called solenoidal, irrotational or conservative. It's not rotating and it's conservative. So a definition of a conservative field if and only if it's conservative. So the H field's not conservative, okay? Because it's not conservative if you have a current source. Okay, now we move into Ampere's law. So you've had Biot-Savart's law, right? Okay. So you took, it was applied to a line of current. So I'm pretty sure Professor Durgan probably covered this, but if you have a line of current and you set up a coordinate system, x, y, and z, this line of current has what kind of symmetry? You have three choices: Cartesian, cylindrical, or spherical. cylindrical symmetry. Okay, is there going to be any variation of the field with Z? It's an infinite line of current. If you go to one position in Z, are you going to see the same field if you go up on it? Yeah, because it's infinite. Is there going to be any variation in theta? No, because if you go anywhere around it, it's going to look the same. So there's no variation in theta, and there's no variation in... so if you want to calculate the H field, it's only going to be a function of what? R. So it can only be a function of R. It can't be a function of theta or Z. And you should have solved for this using Biot-Savart's law. And you've got the H field is the current divided by 2 pi R in the theta direction, where R in a cylindrical coordinate system is out to a point. You remember that? Well, Ampere postulated a law that the line integral of the magnetic field around a closed path is equal to the enclosed current. That's Ampere's law. How many thought Biot-Savart's law was tedious to get to this point? Did you follow through it? Everybody do the integration? You do source and observer coordinates, and you set them up, and you've got to integrate from minus infinity to plus infinity on Z. And you get this integral that you've got to evaluate that's not, it's not, could you do it on a test right now?
No.
You couldn't do it on a test?
We were studying for another test today,
So you appreciate it's a little bit difficult, right? Well, Ampere's law is the easy way to do it. Okay? So basically, you take the same line of current, and this line of current is facing me. So this is the x-axis, this is the y-axis. So that point means it's coming out of the board. And what Ampere's law says, that the H dot dl, if I take a H dot dl path around this line of current, and I put my thumb in the current direction, okay, the magnetic field is circulating in this direction. So that magnetic field component is going to be an H theta component. So if I do a loop at a constant radius, I would take the integral of H dot dl, and L is just always your incremental change, but you'd essentially you'd be doing a closed integral, and H would be the vector. There's no there's no R component. There's a theta component. There's no Z component. So that's H. And you're going to dot that with DL. And DL in any coordinate system is just the elemental lengths as a vector. So in the cylindrical coordinate system, it's dr for the first coordinate. Okay, it's r d theta for the theta coordinate, and it's dz for the z coordinate. So it's elemental lengths. It's not just d theta, because an angle does not make a distance. You have to put the r with it to get the distance. So r d theta converts this angle change to a distance. So it's elemental distances. So if you evaluate that, the only term is going to be the h theta term is the only term over here. That's going to pick out this one when I do the dot product. So I've got h theta r d theta. And if I do this integration around the loop, my integration's over d theta. It's going to go from 0 to 2 pi. So 0 to 2 pi, it's going to be h theta comes outside because h is not a function of theta. So it comes outside the integral. R comes outside the integral. And we've got 0 to 2 pi of d theta. So we've got 2 pi r h theta. What's that equal to? Well, Ampere's law says that the line integral of h dot dl is equal to the enclosed current. Of a single line of current, let's say its magnitude, I is a vector, its magnitude is I, it's actually in the z direction. So we have 2 pi r h theta equals I. The line integral is equal to enclosed current. So h theta is equal to I over 2 pi r. Or you could say that the h field as a vector is I over 2 pi r in the theta hat direction. So is this easier than Biot-Savart's? Most people, when they do, if you're solving problems, it's usually a whole lot faster to apply Ampere's law to the problem than to try to integrate current elements using Biot-Savart's law. Okay, so that's a line of current. Let's consider a sheet of current. Let's say I have these little current elements coming out of the board. Okay. Yeah, I'll stack them up. So there's a current density on this boundary. So that current density is Js in magnitude, and let's put it in the z direction. So let's make my coordinates where this is x and this is y. So we're going to do the integral of h dot dl, and we're going to do a rectangular loop. This has sheet of current. So I can pick the path. I'm going to pick a path like this, and I'm going like that. So let's say the field on this side is H2. Let's see, the field on this side is H1. So this is, on the left is region 1, on the right is region 2. And this is a vector field. So is this field a function of y? It's an infinite sheet of current. It's not a function of y, right? And it's not a function of z because it's infinite in the z extent. So it's infinite in y and z. So the only thing it can be is a function of x if it's a function of x at all. But it's an infinite sheet. Now, do you recall applying Coulomb's law for a layer of charge, an infinite sheet of charge? And the answer is the surface current or the surface charge divided by 2, half the surface charge. Okay, I don't know if you got into boundary conditions, but there's a jump equal to the surface charge of field one side to the other, points out on one side and away from it on each side. It's analogous almost to the completely to the H field case. So basically we do this loop, and if we do the loop, let's go ahead and do each side. Okay, well, I'm going to make this just really small so there's essentially no contribution from that element. But even if I did have a contribution from that element, the path going this way is going to cancel the path going that way because they're the same. There's no change. So the only contributions I get are from the vertical sides on the right and on the left. So if I take the integral around a closed path of h dot dl, and in this case my dl is this vector. So along this path it's a y component, so it's dy. So it would be h2 x component, hx in region 2, y component, because this is the H field. If I do the dot product in this direction, it's only the y component, and it's going to be dy. And I do the other, it's going to be hy in region 1, and it's a minus dy because the dl along this path is minus dy. What's that equal to? Well, let's say this current density, I want to integrate it over this path. If I integrate it over the path, over this distance, that's adding it up over the y distance. So the current that would be enclosed would be Js dy, is the amount of current enclosed. Because just this current density times the length I use, right? So this says that h of y in region 2 minus h of y in region 1 is equal to Js. Can the H field be 0 in either region? Give me an argument why it has to be, the magnitude has to be the same on each side. Direction's different, but the magnitude has to be the same.
One single current?
It just looks the same, right? It's the sheet of current, so the field magnitude on one side, the other side is going to be the same. Direction's different, okay? So this boundary condition, the way we state it, we say that H tangential in region 2 minus H tangential in region 1 is equal to Js. What this says is that the tangential component of the field And by tangential to this boundary, I mean this is a tangential component, that it's going to be equal to the surface density. So the only answer is what for the magnitude of H in either region. If it jumps by, and remember what it was for a sheet of charge. So for a sheet of charge, it was a surface current, or the surface charge divided by 2, and here it has to be the surface current density divided by 2, right? So it's a surface current density divided by 2. So H2 is going to be equal to JS over 2. Which way does it point? Use Ampere's law. If the current's in this direction, the field points in the direction of your fingers. When you're doing this loop, the field's pointing up. That's in the y direction. So here's H in region 2, and H in region 1 is going to be JS over 2, and in the minus direction. So to see again which way the field points, put your thumb in the direction with your right hand in the direction of the current, and it's going down on the left side. Down is in the minus y hat direction. So now look and see what's cool on the boundary conditions. If you look at the difference between these, you've got JS over 2 going up, you got minus JS over 2 going down, so the difference is JS. So that anytime you have a boundary conditions are a really neat way to work problems. Sometimes you can do it just by boundary conditions. I'm going to do a couple more following this, but you'll find there's a vector form for this boundary condition that H tangential in region 2 minus H tangential in region 1 is equal to JS. So that's one way of saying it. Or you can do N cross H2 minus H1 equals JS is a vector. This is the vector form. This is people struggle with, but there's an easy way to look at it. First off, what special relationship does a unit vector along the normal to the plane? We did this plane of current with a current coming out of the board. So the normal vector goes like that in region 2. Okay? So what relationship do we have between N and H and J? Does anybody see what I'm getting at?
They're all perpendicular?
They're all perpendicular. N hat is perpendicular to a unit vector along H, is perpendicular to a unit vector along J. They're all perpendicular. So what this means when you apply the boundary conditions, just remember that. If you have, not only are they perpendicular, this is a right hand set or rule. By that I mean that N crossed into H as unit vector is J. H crossed into J is equal to N. And J crossed into N is equal to H. Anytime you're going ahead, N crossed into H is J, H crossed into J is N, J crossed into N is H. They're all going this way. So if I give you a normal to a plane in the H field direction, you can tell me the current, because you know the current is N cross H. In this case, we had H hat in this direction, N in this direction. Which direction is the current that caused it? Well, you take N crossed into H and you get J. And the current's pointing out of the board. So you can use this relationship to get the directions, make sure you have them right. There's no excuse on a problem of making sure you have things wrong. If you know any two vectors, do the cross products, you can get the others. So we have a sheet of currents coming out of the board. And the current density is Js, and let's say it's in the Z direction. So Z is coming out of the board. And let's say I have another plane of current, infinite plane of current. Current's going, put it over here. Current's going into the board. And XY, so Z's coming out of the board, it's going into the board here. So this is JS Z hat minus. So they're the same current density, and you think of it as current flowing down two conductors, they're infinite. What's the magnetic field that's set up? What's it look like? So basically, if put our start of our coordinate system here, so this is x equals 0, and let's say this is x equal d over 2, and let's say that this point right here is x equal minus d over 2. In other words, the separation distance between these is d. So let's look at the field for x less than minus d over 2. So that's this region, x minus d over 2 would be to the left of the left plane, infinite plane of current. Okay? So the H field is going to be, let's call this 2, sheet 2, let's call this sheet 1. It's going to be the H field from 1 plus the H field from 2. So the H field from 1, we're on to the left of it, so it's going to be JS over 2 minus Z hat. This is H1. H2, we're to the left of H2, so we're doing this by superposition. Linear problem, we can add the fields. So we add H2, and we get plus JS over 2 Z hat. Current's going into the board. The field circulates this way on that one because it's going into the board, thumb in the direction of the current. So the field to the left of sheet 2 is pointing in the y direction. Sorry, this should have been y. And the field for the one coming out of the board is circulating the same way. So to the left of both sheets, I've got JS over 2 as an amplitude. It's going down from that sheet, up from that sheet, so it adds to 0. In between, from minus d over 2 to d over 2, h is going to be the sum of these two. Each one is js over 2, so it's going to be js in the y direction in between the sheets. And for x greater than d over 2, h equals 0. So if you have two infinite sheets of current, you only have a field inside. You don't have fields outside. Okay, we did a line of current. Next one we're going to do is a cylinder of current. So here's a infinite cylinder, and let's say the current flow is in the z direction. This has cylindrical symmetry. If the current flows in the z direction, it's infinite. If we were to look at the current, how do we know which way to do the integration loop to apply Ampere's law to get the whole field? Well, we put our thumb exactly along the line of current. That's the z direction. So in the xy plane, if we do a xy plane cut, and this happens to be the, let's say it's some radius a, and this is JS as a surface current density, and if it has surface current density of that, the total current is going to be 2 pi times JS. Just add it up around the circumference for the total current. So this could have the total current specified, or could have JS specified. You have to be able to go either way. So you have JS specified, and you want to do integration loop. So let's say we do our integration loop inside, right here. And we know that the integral of h dot dl is the enclosed current. What current do I enclose? I did it inside for x less than a, or actually r less than a. For r less than a, h dot dl is 0 because there's no enclosed current. Right? If I do r greater than a, I've got the integral of h dot dl. Well, we've done that a whole bunch of times. You know, it's 2 pi r h theta. Did it for a line of current. And it's equal to the total enclosed current, or it's equal to 2 pi js, whichever way it's specified. So if I do it in terms of total current, it's h is I over 2 pi r theta direction. So it's just a theta component of the current. Exactly like a line of current. You can't tell the difference between whether it's a line of current or a cylinder of current if you're on the outside in terms of the field. You've got to be careful, because if you get a problem in terms of current density, it would be the 2 pi's would cancel. Then 2 pi AJS, because it's when you do the surface current density, you have to do the angle and the radius to get the total. I forgot the A. So this ends up being, if you do this, it's going to be A over R. The 2 pi's cancel, JS in the theta direction. So you got to be careful whether you got total current specified or just the surface current density specified. Last case, or next to the last case. Let's say you have an infinite cylinder to infinity each way, still along Z direction, and let's say the current is completely going in the theta direction. So let's say this is just a J theta current going in the theta direction. So let's take a cut to where it's flowing into the board on this side and out of the board on this side. So you know that if this is surface current density J theta, you know the field has to jump by J theta going from outside to inside, and has to jump by, again, going across here because of the boundary conditions. So you apply Ampere's law. You put it in the direction of the current flow. So if you're doing the direction of the current flow, you would actually apply Ampere's law this way. It would tell you which way the field's circulating. So if you were to do a rectangular loop going up and going down, this is analogous to the double sheet case. To do it precisely, you have to use Biot-Savart's law. It's really hard to do. But I'm just going to tell you what the bottom line is, and you can check on it. I think it's covered in your Hyatt and Buck. It turns out it jumps by JS, that outside the H field is equal to 0. On this side, H field is equal to 0. And inside, outside, fields here cancel the other field just like they did for the other case. These fields add inside so that the field inside H is equal to J theta, and it's in the Z direction. So inside the field is in the Z direction, because the only component you have going up, I put the axis of the cylinder in the Z direction. Now the practical example of this is something that you get all the time in electronics. Here's an infinite solenoid. You try to wrap an inductor or solenoid, and you've got current flowing through it. Well, that can be modeled as a cylinder with 2 components of current. It has one component of current that's a J theta term. It has another component of current that's a J Z term. It's impossible to wrap a solenoid so you don't have both terms. So the JZ term gives what kind of fields inside the cylinder? None. Okay, it's just like the cylinder case we covered before, where the current is vertical. There's no field generated due to the JC component inside, only outside. Okay, it just looks like a line of current outside. So it's circulating in the XY plane. What kind of field is generated from the H theta term? Well, that's the case we just did, and the field's in the Z direction. So what happens, you have inside, you have an HZ pointing up. Outside, you don't have anything from that theta term. and outside you have a H theta term. This H theta term is caused by JS or JZ, and this HZ term is caused by J theta. So if you could wrap a perfect solenoid, you wouldn't, like at a starter coil or something like that, you want to confine the magnetic field. If you could wrap it perfectly with no lead, you wouldn't have any field outside. But you can't wrap it perfectly, and because you can't wrap it perfectly, you get field outside and can affect other things and things like that. You know, some magnetic effects from it. Or if you wrap an inductor, if you could wrap an inductor around a form, wrap it perfectly circular without any lead, which you can't do, you wouldn't have any field outside. Now, you always have field outside if you have it truncated, but I'm talking about in the infinite case, because when it's a short cylinder that has both axial and circumferential components, you have mixed fields towards the end. It's kind of complicated. Okay, any questions? So we've covered Ampere's law. We've showed how Ampere's law is one side of Stokes' theorem. By Stokes' theorem, you can evaluate H dot dl two ways. You can do the curl over the area, or you can do del cross H over the area, or you can do it as a line integral. Most problems you do, you're going to apply either boundary conditions or you're going to use a circuit form of Ampere's law and do it the way I did in these last examples.